Where are we going? Here on the ground it's easy to navigate. We have roads, buildings, signs that can all help us reach our destination. However, in the air we do not have access to all of these cues, and sometimes we are required to fly without any visual reference, only by using the instruments. That's why aviators, since the beginning of flying, saw the necessity of a reliable direction system, independent of the external environment. Left, right, in front or behind, all of these directions are relative, and to give them meaning you need a reference point. And in aviation we need a reference point usable by everybody around the world. Let's take this aircraft as an example. Imagine that he wants to reach the airport that is on its left. If he is very close to the airport, he has probably visual reference with it and can easily tell that it's on the left, and he will start turning and pointing towards it. If it was further away, he will still be able to navigate towards it by reference of the ground features such cities, monuments, hills, roads, lakes, etc., and be able to reach the destination. This way of flying is called visual flight, and it's very often performed by small light aeroplanes. However, sometimes we need to fly in bad weather and in areas where we don't have many visual ground references. Even if we knew where the airport was, without a proper direction system, we were very likely to be drifted away of our track. Like the aeroplane that is in the drawing, which now has been drifted away from the route and now has no idea of where the airport is. This is why we need a direction system that is possible to use without external visual references. These are the three main characteristics that we need for our reference system. It has to be in a relatively fixed position. We don't want a reference that is always changing its place. It should be usable everywhere around the world, both for safety reasons and for standardization. Lastly, it should be able to be measured or sensed from inside of the cockpit in order to determine our direction. Currently there are two main reference systems used, the geographic and the magnetic. The Earth itself is the most reliable reference that we can use, since it's in a fixed position and everyone in the world can use it. However, which of all places available around the world shall we use as a reference? Well, we all know that the Earth is a sphere with an axis around which it rotates, and we took the points of intersection of this axis respectively as the North Pole and the South Pole, and the line between the two as the equator. Through directions, use the geographic North Pole as a reference to determine a defined course, a defined direction. Indeed, most of the charts and the maps are aligned with the geographic north and are the simplest way of measuring a course from a place to another. There are two main types of direction systems used in aviation. The first one is called the cardinal system. It has the north direction pointing towards the North Pole, the south direction pointing towards the South Pole, and east and west along the equator, east being towards the rotation of the Earth and west the opposite direction, with of course northwest, northeast, southeast and southwest in between the four. The only problem of this method is that it doesn't give a very good accuracy, and it's only used in aviation to give approximate directions towards some features. This is why for navigation it has been invented the sexagesimal system, which is very similar to the cardinal one. We have the north, south, east and west in the respective positions. However, here we have the circle that is divided through 360 degrees with the 360 on the top, and each degree representing a defined direction or course. This is a very accurate method and is the main one used for navigation. How do we measure these directions? Imagine a pilot who wanted to fly from Oxford to London. He will simply need to draw a line on the chart and measure its angle compared to the north to obtain a true direction, a true course. However, there is a problem with the true direction systems, and occurs once we are on the plane. The pilot here has no way to determine where the true north is. It cannot be sensed by the aircraft. Indeed, no compass can point towards the geographic poles. Currently, there is only one equipment that is able to sense the true directions, and it's called IRS. This equipment is able to sense the rotation of the Earth and therefore determine the true north and our true heading. However, this is a very complex and expensive method, and it's only used by airliners. To summarize, true directions use as reference the geographic North Pole, which is in a fixed position, which is possible to use everywhere around the world, but however it's not possible to be measured or sensed from an aircraft equipment, except without some very complex and expensive methods. This is why we decided to use magnetic directions to navigate. It has been known for hundreds of years that it's possible to navigate and to maintain a fairly constant direction by making use of the Earth's magnetic field, and has a magnetic North Pole and a magnetic South Pole, just like a magnet, which are actually in a very close position to the geographic ones, from which magnetic lines exit from the southern pole and enter the northern one. If we were to hold a freely suspended magnet, it will tend to align with these lines, pointing to the magnetic North Pole, giving us the direction of the magnetic north, and therefore we can determine our heading, our course and our track. This instrument is called compass. Even though in a very close position to each other, the geographic and the magnetic poles are in different positions, which may cause some differences between the magnetic and the true directions, and it's very important for a pilot to be able to convert from one to another. Imagine this is the Earth, and we have the geographic pole in this position and the magnetic pole in this position. They are very close to each other, but in two different places. And if we were in this aircraft pointing towards the north by reference to our compass, a heading of 360 magnetic, this would not match a true direction of 360. This will be the 360 true, pointing towards the geographic pole. As you can see, there is an angular difference between these two directions. This difference is called variation, and it varies from a place to another. Magnetic variation is expressed in degrees, either easterly or westerly, depending on whether the magnetic pole is to the east or to the west of the geographic one. And it is used to convert from magnetic directions to true directions and vice versa. As a rule, if the magnetic variation is easterly, the magnetic will be least. The magnetic direction will be smaller than the true one. If the variation is west, the magnetic will be best. The magnetic direction will be greater than the true one. In our example, the variation was west, therefore magnetic best, the magnetic direction will be greater than the true, so the true will be less than the magnetic. By how much? By the angular difference between the two poles, which was 10 degrees. So the true direction will be 10 degrees less than the magnetic one, 350, 350. Now I will show you a little bit of a more practical example. Let's say we want to perform a flight from this city, Alghero, to this city, Olbia, through this route. This chart is aligned with the true north, shown by these blue lines called meridians, which all converge towards the North Pole. So this over here will be our true north. Now, to measure the direction of our route, we simply have to measure the angle between the true north and our route direction. In this case, it's roughly 80 degrees, and therefore our true direction will also be 80 degrees, 080. Now, to obtain the magnetic track that we are going to use once in flight, we need to apply the magnetic variation, which is found on the other side of the chart, and it's due east for this area. Variation east, magnetic least, therefore the magnetic direction will be lower than the true. By how much? 2 degrees. 078. Magnetic that we are going to use in flight. Indeed, Almost all the flights are performed with the use of magnetic directions, and all the ground navigation aids are calibrated to magnetic north. Unfortunately, there is a place where it's not possible to use magnetic directions, which is in a very close position to the poles at very high latitudes, roughly above 70 degrees north and south. This is because at these latitudes the magnetic lines are almost completely vertical and so tight together that they do not give enough directivity to give reliable directions to the compass. The compass is not able to determine where is the North Pole. Usually pilots do not fly in these regions unless we have IRS equipment on board, which can let us use the true north. So to sum up, magnetic directions have a reference relatively fixed, which is possible to measure or to sense from inside of the plane through the use of the compass, and it's usable almost everywhere for the exception of very high latitudes. And because of these characteristics, magnetic directions are the standard for in-flight navigation. Now I'm going to show you quickly what are the instruments on board that can help us to find the magnetic directions. These are the properties that an onboard instrument should have. It should be very stable, it should be very sensible in changes of direction. A pilot wants to know promptly if the aircraft is drifting off track. It should be able to self-align with the magnetic north and should have as few errors as possible. Starting with the direct reading compass, this is the most basic instruments to determine heading. It consists of an assembly of magnets which align themselves with a local magnetic field. The magnets are located inside of a case with a liquid which helps it to stabilize. It's a very simple and not expensive method of finding magnetic direction, and it's found on most aircraft as the standby instrument or as the main instrument in some light airplanes. Why as a standby instrument and not the main one, you may ask? Well, unfortunately, it is very unstable and suffers from many errors, some occurring only during turns, accelerations or decelerations of the aircraft, and some that are always present due to interference from the airplane's electrical equipment. It will give reliable information only when in a straight and level flight. Once performing any maneuver, it will give unreliable information about the magnetic heading. Therefore, the properties of the direct reading compass are: it is able to self-align and is very sensible in changes of direction. However, it has many errors, some that are not even possible to correct, and it's not really stable, especially when performing maneuvers. This brings us to the second instrument that we're going to see, the directional gyro. A gyro is an object consisting of a wheel spinning at a very high velocity, and because of this high velocity of the wheel, it tends to remain fixed in space, always pointing in one direction, even if the case or the aircraft around it turns and changes in attitude. Therefore, if we can align a gyro with the magnetic north, then we are able to determine our heading. And this is exactly what we do with the directional gyro. By reference to the standby compass or other ground features, we align the gyro with a magnetic north, and now our magnetic heading will be shown on a compass rose connected to the gyro like the one shown on the picture. Gyros are very stable instruments, however they do wander sometimes. They change slightly in direction, especially during very long flight. Therefore, the pilot must always be checking that it is aligned with our standby compass and eventually correct it. So, to summarize the properties of the directional gyro, unfortunately it is not able to self-align itself with the magnetic north. We always have to align them manually by the use of the compass. It is sensible in changes of direction, and it's very stable now, and only have a few correctable errors. So, if you have a look at it, you see that the compass, it's able to self-align, but it's not stable and it has a lot of errors. while the gyro it's not able to self-align, but it's very stable and only has a few errors due of the fact that it's not able to self-align. So why don't we combine them together? And this is exactly what the gyromagnetic compass does, which is the third instrument we're going to see. As I just said, the gyromagnetic compass is composed by a directional gyro and a compass, and they correct each other's errors. The gyro is fed of information from the compass, which is located on the tip of the wing, away from the aircraft interference to reduce as much as possible the errors, which constantly aligns it with the magnetic north, correcting the wonders of the gyro. The errors of the compass that are present during turns, accelerations and decelerations are damped by the stability of the gyro, which will maintain its direction even though the compass is momentarily destabilized. So what we have now is one of the most accurate instruments possible for navigation. It's able to self-align, it's sensible in changes of direction, contains almost no errors, and it's really stable because of the gyro, and this makes it one of the best choices for an aircraft manufacturer and for the pilot, of course. Lastly, I'm going to briefly show you how an inertial reference system, IRS, works. Basically consists of a platform composed by gyros and accelerometers, which sense the Earth's rotation during alignment to align it with the true north, and the Earth's rotation and acceleration to determine its direction and also the changes in position. All of this information is transferred to the aircraft's computer, which also with the inputs from other equipment can give heading, track, speed, position and even the wind component. This is one of the most accurate instruments. However, a lot of precision is required, which makes it really expensive, and therefore is used only by airliners. I hope you found this video helpful and interesting. If so, thank you very much for watching, and subscribe for more.